Hey everyone, welcome to APHTP String Seminar. Let me introduce today's speaker, Ying Zhao from KITP. Today she will talk about collisions of localized shock and quantum circuit. Please join me in welcoming our speaker, Ying.
Hi everyone. First, I want to thank the organizers to give me the chance to speak here. Today I will talk about it's about some recent work. It's about collisions of localized shocks and quantum circuit. It's based on some recent work with Felix Hill. If time allows, I will also talk about some more recent work that may appear soon with Gary, Henry, and Lionel. So first, I want to give some background and motivations. It's well known that two distant black holes can be connected in the interior through a wormhole. And such an Einstein-Rosen bridge can be interpreted as an entangled state. And this is a famous statement of ER equals EPR. And here's the Penrose diagram. From the Penrose diagram, it's clear that you cannot send signal from one side from the other side. But if you send in two objects, if they're falling in at appropriate times, then they can actually meet in the interior. And this actually poses a mystery, because two signals sent in from the two different boundaries looks like they can meet in the interior if you trust bulk geometry. On the other hand, there are no boundary interactions. So what governs the law according to which the two signals interact? I mean, quite often people will say that Romeo and Juliet jump in and start their happy journey together. But if you think about it more carefully, it's naively, it seems like they won't even recognize each other because they come from two different universes, and there are no interactions between the two universes. So in this talk, we will try to attempt to answer this question from point of view of quantum circuit. I should point out that recently there are some very interesting works involving black hole interior from other point of view, from point of view of operator reconstruction or RG flow, or or from a more algebraic approach. So there is a simplified picture. So before I go into details, I would like to show you a simplified picture of two perturbations ballistically spreading through a quantum circuit with a spatial extent. Let's say, I think the idea will be, the meaning of this picture will be clear later. Roughly speaking, you have perturbation, then it spreads as time increases this way, and this is x direction. And this guy spreads this way. And in this case, they do not overlap. And in this case, the two perturbations overlap. The proposal is that in this case, the two signals actually do not feel each other. But in this case, the two signals will interact gravitationally. So here's the outline of the talk. I will discuss a meeting in the interior of a wormhole and overlap of perturbations in a quantum circuit. I will first review collisions between spherically symmetric shockwaves in ADI-sized black holes. Then I will discuss collisions between localized shocks. That's the most interesting case. At the end, I will point out some future directions and unanswered questions. So first, bulk tensor network and quantum circuit. The bulk geometry reflects a minimal circuit preparing the state. And we can look at a particular case of a thermal double. And we will represent thermal field double by a certain number of Bell pairs. And then these orange dots represent the gates you can apply to this state. And notice that once you have maximally entangled Bell pairs, there is there's one crucial feature about this state. That means that if you apply unitary operations from side A, or you can apply unitary operations from side B, they can be undone from either side. And what that implies is that, let's say Alice has applied some operation, but later she come back and look at her state. There's no way she can tell that she has ever applied this operation. Same for Bob. But once Alice and Bob come together, and then they can notice that someone has already applied these gates. So in this sense, these gates does not belong to Alice's subsystem. It also does not belong to Bob's system. These gates are only meaningful when you have Alice and Bob system, Alice and Bob with their subsystems together, and correspondingly, people have shown that as we apply more of these gates, this part of geometry is getting longer. And it's well known that this part of geometry is outside Alice entanglement wedge. It's also outside of Bob entanglement wedge. It's only inside the entanglement wedge of Alice system union Bob system. So we see that there is a certain match of properties between quantum circuits or quantum gates and gravity. So the rough idea is that once you have entanglement, you have shared quantum circuit, and shared quantum circuit will correspond to shared bulk region, in the sense that this region is actually accessible from both Alice and Bob, in the sense that they can jump in. And we can do we can do more. We can perturb thermal field double. The perturbed thermal field double was described by an epidemic model. Roughly speaking, we represent the perturbation, let's say by extra qubit. And the reason we represent perturbation by extra qubit is because we know that the perturbation will increase thermal entropy. So it makes sense to represent the increase of thermal entropy by something extra. And you imagine this extra thing carries some disease, and any qubits that interact directly or indirectly with the perturbation will get perturbed relative to original circuit describing the thermal field double. And it's also intuitively clear that anything affected by this one can no longer be undone from Bob's side, because Bob has no access to this. So, but actually the property we will need to use in this talk is about these unaffected quantum gates. We will call them healthy gates. A crucial property is that, so notice that this circuit model essentially comes from studying, let's say, super Yang-Mills or string theory or a matrix model. So we know that the dynamics of a black holes, they are, first of all, they are chaotic. Then they are also k-local, in the sense that each degrees of freedom only talk to the other k degrees of freedom at each time step. That's why we model the dynamics this way. But because of these properties, there is one crucial feature is that even after the perturbation comes in, there will still be healthy gates. And because the perturbation takes time to spread, so these healthy gates will correspond to this shared interior region, but it's after the shockwave come in. And later we'll focus on this region. It's shared region, but it's after the shockwave comes in. As we said at the beginning of the talk, we will be interested in, let's say, how the interaction happens. We'll be interested in how the collision happens. So we consider quantum circuit with perturbations from both sides. Let's first look at ADS-sized black holes and almost spherically symmetric perturbations. If you draw the perturbation, it's clear that depending on the arrangement of a time, let's say if TWR is larger than minus TWL, if you arrange time in the appropriate way, then the two perturbations actually, they do not have overlap in the quantum circuit. And correspondingly, the signals sent into the bulk hit the singularity before they have a chance to meet in a wormhole. A more interesting situation is obviously the case that when there is a region that the two perturbations actually have some overlap. We mean that there is a certain part of a circuit where both perturbations appear. And the proposal is that they actually correspond to the case where the two perturbations actually meet in the interior. And at this stage, it should be intuitively clear that if we want to ask the properties of the collision, we should study this part of the circuit. The collision property of the collision is somehow encoded in this overlap region of the circuit. And the larger the overlap is, the stronger the collision is. Actually, one can make, yeah?
Sorry, I have a question on here. So
Yeah. By the way, I encourage questions, so please go ahead and ask questions. Yeah.
On the right diagram, the shock is now they really beat each other, like there is scattering. There could be scattering, but on the left diagram,
I see. Do you want to say that it actually looks like there's no real overlap?
Yeah, so that's my
Okay. Yeah. Good question. Here's the reason. The reason is that this is an artifact of drawing the pictures this way. You imagine what will happen in an extra Hamiltonian system. It's like you send in the perturbation, and then you wait for a tiny bit of moment. At the next moment, actually, all qubits will be affected, but they are all affected by a tiny amount. And then it's gradually, and this amount gradually increase. So that's why. But when I draw the picture, I don't know how to represent that everything is affected, but only by a tiny amount. So I just draw a picture that they only affected a few of them. Good question. This is I would say that this is this is a limit of a circuit model comparing with the actual Hamiltonian system, because actual Hamiltonian system, it's really at the next step everyone is affected, but only by tiny amount. Thank you for the question. So one can diagnose a collision by looking at the size of operator preparing the state. And the computation reduces to computation of various 6-point functions. If you are interested, you can look at the paper, but I won't go into the details in this talk. In this talk, the question I will be interested in is this. I want to know about the properties of this collision, and but what to ask. I do not have an S matrix. Unfortunately, the collision happens inside the interior. So I will ask about something else. I will ask what's the space-time geometry look like in the post-collision region. And from we discussed before, this region more or less will correspond to the healthy gates in this overlap region. So the first quantity, basically, it's the simplest thing is just we can just compare. What we do is that we will compare the number of healthy gates in this overlap region and see how this depend on time. Then we will look at, let's say, certain quantities, maybe spatial volume. I mean, in the paper, what we did, we compute space-time volume and see how they depend on time and do a comparison of these two. Before we start, just notice that everything is only a function of delta t, where delta t is the amount of overlap. From circuit, this is obvious by translation symmetry, and from the bulk part, this is a result of boost symmetry. So,
question.
Yeah.
I think this question is somewhat late, so I'm trying to understand the first question itself. So here you are trying. So we have CFT-A and CFT-B, and
yes.
we have a self-field double state.
Yes.
And we trying to evolve such a state, and we have some final something state. Then what do you want to reveal in this? So what is the object of this kind of discussion? So inside collision,
the question is, I want to see how the collision, what governs the law according to which the collision happens. How do they interact? Because there are no interactions between CFT1 and CFT2. Yes. But the two objects, they collide and they interact. The question is that how do they interact? And my answer will be that even though they don't interact, they share some quantum circuit. And these properties of collision is encoded in this shared quantum circuit.
And what is the result for the boundary CFT? So for the Sommerfeld double state, as a
for the Sommerfeld double, think about them as the Sommerfeld double has some entanglement.
Yes.
Because they have entanglement, there are operations that their quantum circuit that are shared between the two sides.
So you want to reveal the origin of the entanglement to maybe
No, not the origin of entanglement. You create the entanglement. But once you have entanglement, I want to show that once you have entanglement, how do they give rise to this meeting in the shared region?
I see. So that can be interpreted in this way. That's why.
Yes.
Okay,
yes. It's once you have shared, the entanglement is there. That's the input. But it's now clear that if you have, even if you have entanglement, how do they meet in the interior? Because they do not interact.
I see. Okay. Thank you.
Yeah. Thank you for the question. So for the purpose of later discussion, we will consider the case where the scrambling time for the two signals are significantly different. The way we achieve this is that we adjust the strength of the perturbation. We make the strength of the first perturbation significantly smaller than the strength of the second perturbation, such that, let's say, this one carries one piece of epidemic, but this one carries delta S epidemic. So at the end of the day, with such arrangement, the scrambling time for the first one will be twice of the scrambling time of the second one. This is just basically the most general possibility you can have in the spherically symmetric perturbations. And if you draw quantum circuit, so this is just, I will no longer draw those circuits with dots, just the meaning should be clear that the perturbation comes in and spread, perturbation comes in and spread. You will see that there are actually 4 different regimes. During the first regime, when delta T is small, this part actually grows linearly in delta T. And what happens in gravity in this regime is that you can basically ignore back reaction. And as delta T increases, this point, the collision point, will move down. And at this point move down, this post-collision region will grow. In the second maybe I think it's easier to first look at the third regime. In the third regime, when delta T is large enough, you'll see that this part actually, this overlap actually start to shrink as you increase delta T. And what happens is that this point is already very close to the bifurcating surface. You can just basically consider it sits at the bifurcating surface. However, because of the back reaction, the singularity will bend down, and that will make this post-collision region shrink. And once this overlap, this delta T is really large, then from circuit point of view, they're basically normal healthy gates. And what happens is that the collision is very strong, and this point, the collision point, is exponentially close to the singularity, and this region is very small. There is another interesting regime I ignored earlier, is that these two effects can actually balance out each other. In the case when the two scrambling times are different, you can see that when delta T is between these two scrambling times, there is a situation like this. In this situation, when you increase delta T, this part no longer changes because it can never larger than T star 2. And in the gravity side, this corresponds to the situation where the two effects balance out each other. And honestly, when I find this, I was a bit worried that if the gravity will exactly balance out each other to reproduce the circuit result. But at the end of the day, here is what we get. This is a plot with different parameters. I think it should be, on the scoring, it should be clear that actually each line is secretly 2 lines. There is a solid line and a dotted line. The solid line is a result from circuit estimate. The dotted line is the result from gravity calculation, and somehow they match pretty well. I should point out that the only regime that the match is not that well is during the first couple of thermal time and during the regime, roughly speaking, 2 scrambling time, where the transition happens.
I have a question in the
yes.
regime, in the previous slide.
Yeah.
The last region where they are this. The D in the case, the singularity is very close to the.
Yes, the singularity is close. So, are you trying to ask why does the singularity bend down?
Oh, no. My question is if that is the case, I guess this is kind of the shock is calculated by classically, like using the geometry. So if that shock is very close to the singularity, there's some like a further this gravity is too strong, so that this kind of
very good question. I would say that among the four regimes, this regime is the least understood, but it's also the most interesting one. And let's say if you look at the plot, it's clearly that there's some transition happens here. But what happens is that after this, the circuit prediction gives you exponentially small result, exponentially small in time. And the bulk calculation also gives exponentially small result. They match in the sense that they both decay exponential in time. They don't match that well in the sense that the coefficients do not really agree. And what's worse is that it's always dangerous to compare to exponentially small things. So, and you are absolutely right that people expect various corrections from gravity, from various stringy effect will become important. And actually, in that, if the collision becomes really strong, it's not even clear if Einstein's equation is still trustworthy. But unfortunately, we have very little understanding about that, and it's not clear what's the right tool to explore that. Simply because no matter from geometry or from circuit, which is a more boundary perspective, everything becomes exponentially small. But that's something I have been thinking about. It's just what can we say about it's the most interesting part, but we know too little about it.
So
thank you.
It is a little bit clear that because it's a singularity, one can intuitively say that something should be break down. But in the circuit side, is there a way? Can you see something special happen?
Oh, in the circuit side, it's just basically no more healthy gates. No more healthy gates. You'll see that this part eventually shrink to zero. Then it's basically no more healthy gates. From circuit side, it's clearly there is a transition. I have been counting healthy gates, but now there's no more healthy gates. Clearly there's some transition. But the question is that, okay, no more healthy gates. This is not good enough. What more can we say? That's the difficult question. I don't know the answer, but thanks for the question. I mean, I like to discuss if any of you have ideas. That's definitely the most interesting part. And for the purpose of today's talk, I will mostly talk about collisions between localized shockwaves. That's where you actually see most interesting features actually will be put together. So the localized shockwaves was discussed. Let's first consider one shockwave. Localized shockwaves was discussed by various authors. In particular, I mostly used this paper. So there will be a shift at the horizon, but the shift will depend on the transverse location. So the shift will be the biggest when you are at the source, and it dies away as expected. And in this picture, I mostly basically just took it from this paper. This picture is a circuit picture, and I promise you that I will show this picture again later. But right now, I just want you to understand this, that it basically just shows two cones. This one is a causal light cone. This one is something so-called a butterfly cone. So what happens is that the perturbation will stay inside the causal light cone, just because of causality. Nothing can spread faster than speed of light. But its effects will stay very small until reaching the butterfly cone. That's why I use different color. And for generic dimensions, these two velocities will be different. That's why they have different slopes. This is a circuit analysis from the study of a single shockwave geometry. How about collisions of localized shockwaves? What we will do is that we will, because there is a transverse direction x, we will focus on some particular x. And with slight abuse of language, we will call the distance between causal light cone and the butterfly cone T star. And notice that this definition of T star will depend on X. Now you should see that why earlier I assumed the two scrambling times are different. Because for the case of localized shock, if you look at a particular X, then generically the two scrambling times are different. T star 1 of X, because T star will depend on X. So generically T star 1 of X and T star 2 of X will be different. And this is just write down the expression of this. And what we do is that we will imagine a collision like this. So we fix the impact parameter, and we just imagine that we fix the impact parameter, then we adjust the time separation. And the amount of overlap at time X is here. We call delta T of X. The first regime clearly is when delta T of X is small. Then you will see that we will look at the number of healthy gates at a specific X, location X. Notice that when I say X, I mean a boundary location X. We'll see number of healthy gates at the location of X. Clearly, in this case, this thing grows linearly in X. There is very similar to the story before. There is a certain regime where this part is basically a constant, no longer changes with the delta T of X. And then in the third regime, this part actually decreases in delta T of X. In the last regime, it's if you draw a slice, you will notice that basically no more healthy gates. Because if you draw a slice, no matter where you are, the perturbation, either the red perturbation or the pink perturbation has grown to maximal. So basically, there's no more healthy gates at X. So the circuit analysis is very similar to what we had before. But the tricky thing is about gravity analysis. In general, the metric in the post-collision region is not known. But from circuit analysis, we see that there are 4 different regimes. So we will try to identify different bulk features that are responsible for the different behaviors. First, what gives rise to the growth of post-collision region at a particular X? In order to answer this question, we need to know that where is the shock wave? Because in earlier literature, mostly people study the case when the perturbation coming at a very early time, then they just assume the shock wave is at u equal to 0. But for our case, where u is the critical coordinates. But for our case, we need to consider that the shock wave actually coming at finite time. So u is finite. So my first guess was that, okay, must be given by the surface, given by u equals constant. But that's not right. Simply just by causality, you can see that that's not right. Because you cannot violate causality, but u equals constant is a space-like surface, and that will violate causality. And and then my second guess is that, okay, then it probably will be delayed away from the source, delayed by butterfly velocity. It turns out that after I carry out some calculation, that's also not right. After some calculation, we did calculation in planar BTZ or regular ADS, where you can solve it explicitly. And then you will see that what happens is that away from the source, it as if the signal comes in at a later time. But the amount of time delay is controlled by the speed of light, is not controlled by the butterfly velocity. This statement is not exactly right. Near the singularity, there is it's not exactly right. So it's not exactly given by this line. But for the most part, it is. So what happens is that if we ignore back reaction, then at a different X, we can just pretend a signal come in at a later time. And if we ignore back reaction, this part again it grows like delta T of X. So this is some estimate. In order to check the estimate, we actually did some numerics. Let's look at this thing. This thing is that, let's say we look at the overlap as we change X and see what will happen. You see that as you change X, this overlap will first grow, then stays constant, then decrease. And the plot here is that as a function of X, it grows, then stays constant. I mean, this is only half of a plot. I didn't draw the other half. It stays constant and decrease. And then we can look at this as a function of t. As a function of a t, what you expect is that it increases as t increases. Actually, in this case, it decreases as delta t increases, and then it eventually stays a constant. And this is what we see. In particular, we notice that the slope as a function of x is twice of a slope as a function of this is actually a particular t. This is t. This is TWR. So and that basically shows that it's only a function of a delta t, because we look at it as a function of x, we look at it as a function of t, and we notice that as a function of x, the slope is twice of that as a function of t. So this is just some numerical result to support that the estimation earlier is trustworthy. The more interesting thing, of course, is the shrink of a post-collision region. And since we cannot solve for the geometry, so we need some other estimation. And there is one particular quantity I want you to pay attention to. Earlier, we call h of x is the amount of shift at the horizon. And now we have two shock waves. So there are two shifts. One is h1 of x and the other is h2 of x. If you write down the gravity, if you compute it, it actually have such a simple form. Roughly speaking, this characterizes the amount of overlap in a circuit at location x. On the bulk side, h1 of x times h2 of x controls the nonlinear effects in GR. So if we trust the implication from a circuit picture, it looks like the singularity will bend down, and the shared interior region will become small at transverse location x, where this product becomes of order 1. I find this a reasonable statement because this is exactly when the nonlinear effects of GR becomes important. So this is just to give you some intuition. It's when the amount of overlap in the circuit gets large. That's exactly when nonlinear effects GR becomes important.
Can you explain about this? Oh, I see. I about to ask what is the H1 and the H2.
Okay, I'm sorry. So h of x is this shift, and h1 is here, h2 is here.
I see. So why do you multiply them to?
Okay. So, the reason I look at them is because I asked Douglas Stanford, and he said that that's an interesting quantity to look at. And when I multiply them together, indeed they have a specific simple form like this. And maybe after I give you some, maybe after one slide or two, it will be clear that why the product of them is an interesting quantity to look at.
In the geometry or the circuit?
In the circuit, it's clear that why it's interesting, because in the circuit we see that this thing, roughly speaking, is it gives you the probability of overlap.
Yes.
In the circuit, it should be clear, but in geometry, why is it interesting? I will show you later.
Okay, thank you.
Yeah, in geometry, so what we will do is this: we consider a family of null geodesics in this direction, family of null geodesic, and we look at Ricciardo equation. And for those of you who are not familiar with Ricciardo equation, it basically tells you that how this family of geodesics, how the congruence of geodesics, how the transverse area changes as we propagate forward. And it should be intuitively clear that because the gravity is attractive, so the family of geodesics will be attracted together. And once we have matter, because gravity is attractive, the matter will help them to focus. And what will happen is that if you write down Ricciardo equation, you'll notice that there is a shock wave here. And once you go across the shock wave, the expansion will jump. And once the expansion jump, that will make the family of geodesic focus more. That means the affine distance to the singularity will become smaller. So we can bound this affine distance L by this h of x by some calculations. I won't go over the details. But there is one problem here. This is well known that null affine distance has no physical meaning, because it depends on the overall normalization of this I mean, this is not a proper distance. This is only an affine distance. It has no physical meaning. So we can bound this 1 over, it's bounded by 1 over h1 of x, but it's undetermined up to a constant. But the thing is that once we have two shock waves, then we can consider two vectors here. And we normalize the two vectors such that the product is equal to, let's say, minus 2L squared. This is just a matter of convenience. You can call it minus 1. And once you have this, you notice that there is upper bound of this affine distance, L1 times L2, which is basically given by 1 over H1 over H2. And I hope in this sense, I could see that why, I mean, the product of them is something that actually interesting. It's if you just have one of them, then if you, I mean, in critical coordinates, it's a shift by h1 of x. But if you change your coordinate, amount of shift will be different. But once you multiply them together, it's something that with physical significance. And I hope it should be intuitively clear that, so I want to admit that we don't have a rigorous proof. But at this stage, it's already clear that when h1 of x times h2 of x becomes large, that means the product of this guy times this guy, L1, L2 will become small. That's why this region will become small. And the problem is that if we don't put in any constraint in the geometry of this region, we cannot say anything. I mean, you can well imagine you have a geometry where L1 times L2 is very small, but somehow the geometry inside turns out there have region that's very large. But on the other hand, we actually know that the post-Euclidean geometry, it needs to satisfy Einstein's equations in the vacuum. So it cannot be arbitrary. So let's say if we have locally ADS3, we can use the following ansatz. And it's a special situation in 3 dimensions that this ansatz actually solves Einstein's equation. And with this ansatz, with the input that L1 times L2 is upper bounded by a specific quantity, one can actually compute the space-time volume there, and one can show that we actually reproduce regime 3 and regime 4. This change of volume is the change of volume. It's basically the volume at a specific constant x slice, roughly speaking, has the form as we want. In one regime, it decreases linearly in delta t. In the other regime, it decreases exponentially in delta t. And we see the behavior of regime 3 and 4. And actually, if we can do better, if we want to really see all 4 regimes, in order to do that, we need to improve the bound. Recall that when we got the bound, this bound is based on the assumption that the shockwave basically lies at the horizon. That's why we get regime 3 and 4. And in order to improve the bound, we need to consider the case where the shockwave comes in at some finite time. So the collision point, let's assume the collision point has specific coordinates. Then one can relate this product of expansion to these coordinates. I mean, I won't go into the details. At the end of the day, you get a better bound. So here's our old bound. This is a better bound. This better bound is again L1, L2 is bounded by 1 over the expansion, and you get something like this. And once we get this, it actually helped me understand something I didn't understand before. Honestly, when I saw the gravity give a such good match, I was surprised. But once I get this, I see the sum of 4 exponentials. Then I know why we got the 4 regime. It's a competition between these 4 exponentials. And here is a plot of the upper bound on post-collision post-collision volume. You'll see that. So this is a head-on collision, and this is for the case where two signals had the same strength. You'll see that. So this is a 3D plot. This is x. This is t. If you fix s, if you fix a particular x, you see a linear increases, linear decrease. And for this thing, if you fix x, you see a linear increase, plateau, linear decrease, go down. It's at a particular x, we see basically the same shape before. but at a different x, I mean, this entire thing is shifted. We can also consider finite parameter. I mean, this is what you get. Finite impact parameter. I mean, it does not, the collision does not have to be head-on. It's again at you see four regime at a particular x: increase, plateau, decrease. And I will comment briefly on about higher dimensions. In higher dimensions, we assume the following ansatz like this. But the question is that this doesn't really solve Einstein's equation. It solves Einstein's equation to linear order in h1 of x to h2 of x. Corrections are proportional to h1 of x times h2 of x. But luckily, the regime we are interested in are exactly regime when h1 of x and h2 of x starts to increase, but still stays less than 1. So after some calculations, I will just show you at the end of the result. In higher dimensions, one feature in higher dimension is that the butterfly velocity is no longer the same with the speed of light. That's why you see this thing actually bend up. You again see linear increase, plateau, linear decrease, go down. I mean, this picture is actually my favorite plot. The reason is that we can actually do this is a top view of this figure. I think I promised you earlier that I will show the circuit picture again, and here it is. You clearly see that there are two cones with a different slope. But this is not a circuit plot. This is a plot from doing bulk calculation by studying the interior geometry. And somehow these two plots clear. These two plots shows up. So it should be clear that this circuit model just miraculously somehow characterizes the important features about the complicated dynamics of collisions in the black hole interior. This is the most general case. I mean, it's too complicated to really to look at the details. I will just show you this for fun. This is for non-head-on collision, finite impact parameter, and also different initial size, just to show it for fun. And let's see, how am I doing with time? Can I have, let's say, maybe 7-8 minutes?
Yeah, sure.
Yeah. So if I have time, I want to show you one other applications of this. Is about the effect of a charge in scrambling. So the collision happens in the interior, and it should be clear that interior trajectory near the black hole horizon actually has to do with scrambling. And there is a situation when there is something funny happens to the interior trajectory. It's like this. You imagine you have a charged black hole. You throw in something that carries the same charge with a black hole. And you can show that in certain regime, when the charge is large enough, there will actually be a bounce. Infalling charged particles can bounce in a charged black hole. I mean, this was found by Gary and two of his students. Then we try to understand this. Let's see. By the way, one effect of this bouncing is this. You can study the back-reacted geometry and studying scrambling time. You consider two cases. One case is that the particle carries energy E of charge Q. The other case is that the particle carries energy E but no charge. You notice that for the charge case, the scrambling time, it takes longer time for the scrambling time to finish. In a sense, let's say we send in the particle at the same time, but the time when the scrambling is over actually is later for the charge case. And this is the amount of distance, where mu is the chemical potential. And there is a coincidence we found is that you can look at this time difference. We want to characterize how early this bounce happens. And there is one invariant way to characterize how early the bounce happens is, let's say this is t. This is the corresponding t here. And we look at the bouncing time and look at this time difference. I call TD. And there is a coincidence is that as long as the charge, as long as the black hole is not too extremal, is let's say away from too extremal. It's charged but away from completely extremal. Actually, this amount of a delay we find is roughly the same with this. And we call it a coincidence, but this really is not a coincidence. So here's the question. Does the charged particle take longer to scramble? And in order to answer this question, we actually made use of the technique we just used. It's like there's one feature of there's one way to compare scrambling time is that you consider collision, because we see that if the two signals take different times to scramble, then you draw the similar figure as before, you will see a plateau. And if the two scrambling times are the same, then there is a no plateau. So we first consider the case where this guy has smaller energy with this guy. None of them are charged. Then you see that there's a plateau. That means the left one takes longer time to scramble than the right one. The plateau shows that red and pink signals have different scrambling time. Let's look at a case when there is a bouncing. When there is a bouncing, you consider the case that you send in something with energy E, charge Q, and you send in something else with energy E and no charge. And what you get is this orange curve. Actually, there is a delay of scrambling, but there is no plateau. So what do we learn? We learned is that in this case, the two signals actually have the same scrambling time, but the onset of scrambling of this signal is delayed. From the interior circuit, this is what's, the question we ask is that does the charged particle take longer to scramble? The answer is no. The scrambling of a charged object, what happens is that the onset of scrambling is delayed. That's why you see this instead of a plateau. So at the end of the day, I want to point out some unanswered questions, and for discussion, if anyone has idea, I'm happy to discuss, is that so overall, the goal is that to get a boundary interpretation of a bulk gravitational interaction. But one encounters a problem is that what the right bulk quantity to ask about. So when I first worked this out, I was happy. Oh, great, we have a boundary mechanism of this collision happen. Then I realized that, oh no, actually in the bulk, I don't even know what to ask about, because we are so used to S matrix scattering studying. We are used to use S matrix to study scattering. But in this case, there is a S matrix is not appropriate quantity because you don't have outgoing signals. So the question is that how do we characterize collisions happening behind black hole horizon? In what regime does S matrix or scattering amplitude still work? So far, the quantity we have been looking at is the space-time geometry after the collision. But I have to admit that this is not the conventional quantity one usually uses to characterize a collision. So can one make a connection between this and the more conventional characterization of scattering in proper regime? And in fact, in the paper, we did calculations in renderer ADS. The reason we do that is because that in that case, in certain regime, the signal will actually come out. So we are hoping that in some future work, we can do some comparison. And okay, this is a question that Zhang asked earlier. What happens after two scrambling time, which we know that that's the most interesting regime, but we somehow know too little about it. By the way, if the collision happens in renderer ADS, then we know that there will be something funny will happen, is that a real black hole will form in ADS. So we can do the calculation in renderer ADS and pretend there is a black hole. In that case, secretly the signal will still come out, but after that transition, when we claim that the collision, there's no more healthy gates, what will happen is that a real black hole formation will happen. Again, it's some future work at this stage. How to characterize this from quantum circuit, we know very little. And as for my last point is about charge scrambling. Is there a boundary microscopic description of this delay of charge scrambling? And these are some unanswered questions that are conceptually more difficult, but I'm very interested in. One is about the role of singularity. Actually, throughout the talk, I lied to you a little bit in the sense that I basically assumed the existence of space-like singularity, because the existence of space-like singularity will prevent the meeting of signals that are sent in too late. But what about collision near the inner horizon for charged black hole? I mean, do we trust the geometry there? Do we trust the semi-classical geometry or low energy field theory there? We don't know. And how to make this picture of unitary black hole interior as unitary quantum circuit more rigorous? Are there any similarity or difference between tensor network with in the exterior, and how to connect this picture with other discussions of a black hole interior? Throughout this work, I had a fixed Hamiltonian in mind in the context of ADS-CFT, how to incorporate different states of baby universe. And we have been trying to understand matter propagating in the interior in terms of quantum circuit. Then how about firewalls? And that's all I have. Thank you.
Thank you very much for the very clear talk. And please ask for questions. Actually, I have several questions, or if there is, yeah, maybe I can ask several questions first. So, in the gravity side, it's clear that this light cone, because we know the speed of the light is fixed, and the velocity, the butterfly velocity is maybe depending on system. There is some like black hole is fixed. In the quantum circuit, how can we see this light cone and the butterfly velocity?
Oh, in the quantum circuit, this is a sort of a how to say this? In the quantum circuit side, this two cone is an input. It's an input that let's say where's this picture? Yeah, on the quantum circuit side. This was derived from this, but on the quantum circuit side, for the purpose of our work, we take this as an input, and then what we do is just put two such things together and see what will happen. And then what we see that if you have two such things, you put them together, you get 4 different regimes depending on X. But you are right that in the quantum circuit side, the existence of this is an input.
I could see the one slope, but what about the other slope in the quantum circuit picture?
Which flow?
Here there is light cone and also there is butterfly velocity too.
Yeah, I think in the quantum circuit, we don't know how to derive butterfly velocity in the quantum circuit. That has to be an input. So what the quantum circuit can tell you is that at each x, there is still some exponential growth until saturation. But the fact that this velocity is larger than this velocity, that's an input.
Can we go to this quantum circuit like a picture in the previous, in the early?
Yeah.
Yeah. Here, this slope of the red curve, is it?
Yes. Okay. Now you ask. Okay. Now I understand your question. So in this case, one can actually compute scrambling time by assuming that there is let's say we use a simple circuit model given by Hayden and Presco, and we assume that the initial, let's say, size is of order 1, then one can compute the scrambling time. But there is one key thing is that this scrambling time depends on the initial size here, and what's missing in this case is that we know that the signal come here will be a delay, but what's the initial size here? That's what's missing. So that's why this part is we don't know how to derive this. We use this as input and put 2 of them together and see what will happen.
Okay. And another question is.
Oh, by the way, I realized that now maybe there can be a better. You may worry about circuit model is not good enough, in the sense that when we say circuit model, what we had in mind is a boundary quantity. And there's better boundary quantity for this purpose, which is a 6-point function. That's some ongoing work. In some earlier work, let's say if you, let me take this slide. If you want to ask how many healthy gates are here, what we do is that one can do an integral from here to here of the number of healthy gates at each time. And you can see that you can write each time as some kind of size, which is reduced to a 6-point function. So if you are worried that how to get this from quantum circuit, I have to admit that we don't know how to get this from circuit, but I think we will be able to see it from 6-point function. The butterfly velocity will show up in the 6-point functions. Okay, go ahead with the question. I'm sorry.
No, that's okay. Thank you. Another question is, maybe this question is not so relevant to your talk, but
no, that's fine. It's fine.
So people also consider this Sever's wormhole by sending the negative energy shock.
Oh, that's very interesting question. The question is that okay. So that's a very interesting question, and I think it's. I also thought about this. The problem is that how do you send in negative energy shockwave? If you generic perturbation, if you just let's say I start from thermal field double, I just perturb L side. There's no way I can send in negative energy shock. The only way I can send negative energy shock is to couple L side and Bob side, and then that's a traversable wormhole setup. And how to understand that setup in this language is something I've been thinking about, but I haven't really sorted out yet. But that's an interesting question. Presumably, with negative energy shocks, something opposite to this will happen.
Yeah, even in quantum circuit picture, is there no study on that? Like I
don't think there's a known study on that. That's something I'm interested in. I thought about it a little bit and I gave up. I thought about it a little bit, I gave up. But there is no known study on that. That would be an interesting topic.
I see. Okay.
The question is that for that purpose, you would have to couple both sides because otherwise you cannot have negative energy shockwave.
Okay. And probably Maudis.
Yeah, I have a question.
Yeah.
So I think all of these studies can also be formulated. Can be formulated in a stationary way, but instead of like changing time, you can change like the scale and like the scale of two intervals that are mixed together. And for example, there is a wall or a singularity at the end of your bulk geometry. So actually we also have done similar works to this, but instead of formulating this kind of language, we're formulating using mutual information and mixed correlation system. And then instead of HX or delta T, we have, for example, two interval which has width of L and distance D between them. And then all of these scales are just length scales and compared with the position of the wall in the end of singularity, and we can just again derive these four regimes. Also, this work by Zhao, they formulate the same thing by using a number of states like K1 and K2, and instead of your HX, HX1, HX2, they have K1 and K2, which also they also got the same result. So I think for the negative energy in the singularity, you can have like different boundary condition at the end of your wall. So maybe like a energy in the your hard wall at the end of the geometry, and then probably you can study this way, which is much easier, I think, than using dynamics and delta T and shock waves, I think.
Okay, I'm not aware of this, but thank you for you mentioned that there's some work by Xidong. I know that they study mutual information. You see different regimes, you see different transitions, but that's completely different thing in the sense that there's no dynamics involved. And what we are studying is the interplay of black hole dynamics.
It is the same, you know, you are changing delta T, and by changing delta T, you are increasing your ratio in a way, because delta T and the L is kind of the same. You're just kind of a length scale in your system. It doesn't matter if you change delta T or you increase L. It's basically you are increasing this in the thermal field double state. You are actually increasing these two side strand or these two side size. So it's very the same. It's actually similar. It's the same system.
Okay, I can go ask Xidong, and I'm not aware of this, but thank you for letting me know.
Actually, before Zhao, we also calculated this using confining geometry. Other groups also did that. So you have two regions in the boundary. You change the distance between them. We calculate complexity of purification, entanglement of purification, and also for the charge case, we also saw that. We also demonstrated.
I think I know what kind of work you are talking about. Honestly, I really don't see the similarity in the sense that this is about the dynamics, and this delta T, I mean, this circuit is not a geometry that's sitting there. This circuit characterizes the dynamics. It's actually the history of dynamics.
I agree that we cannot see scrambling times, but delta T changing this like size of this shockwave, this is exactly similar. And then you're comparing the size hx, hx1, hx2, and then with comparing with S, I think. Exactly the same thing that Zhao has done, which also we have also done the same.
Okay, thank you for letting me know. Thank you for telling me about this. Yeah, thank you.
And also for the charge case, like for complexity of purification, mutual information, all of this correlation would be suppressed when we have like charged boundary system, or if you have massive gravity, which means that you have dissipation. So
I think we realized that if you compute 4-point function, you can see that the end of a scrambling takes longer. Yeah, the question is that interpretation. We know that the end of a scrambling takes longer because it's suppressed. But now we want a new interpretation. We don't want to say that it's initial. We want to say that the scrambling still takes essentially same time to happen, but it's just one of them starts later. We want a different interpretation.
Yeah, you got the same thing. You got the same. Your result was that charge doesn't increase a scrambling time, which is a little.
No, that's not that. No, that's not what we want to say. We want to say that they have the same scrambling time, but one of them starts later.
Yeah, so that's when I'm a little bit confused because volume, like if you calculate, for example, this volume that you said you calculated, this volume would decrease, right? When you have charge gates. For example, two charges, two charge particle will be interact. So you got a smaller volume inside, right? Is that correct?
We didn't consider that. I don't know. We considered a collision between a charged particle and a neutral particle in order to compare scrambling time. What we want to understand is the effect of bouncing. So we compare the collision, we consider the collision between a particle that bounces and a particle that doesn't bounce in order to compare scrambling time.
Because we calculate complexity of purification.
We didn't consider complexity.
This volume, isn't it essential?
No, we didn't consider complexity.
But isn't this volume?
We consider space-time volume, and that's because that's the most easiest thing to do. But there's no state complexity involved in this talk.
Okay, thank you. Thank you so much.
Thank you.
Hello.
Thank you for the questions.
Hello, Zhao. I want to ask one question. So, I think you said you calculate the 6-point function. And,
sorry, I said what? Sorry. I didn't get what you said.
Okay, I think you in your talk you said that you can calculate the 6-point function like a collision.
Oh, so you mean 6-point function? Yes. For the spherically symmetric case, yes, we computed that. For the localized case, it's some ongoing work. Yeah.
And I also want to know. I think that after you get this correlation,
yeah,
you possibly can know how the gravitational constant renormalized, and you said that you can see the relation to the entanglement. So I want to know whether you can obtain the relationship between the renormalized gravitational constant and the entanglement.
I don't know. I didn't see the renormalization of gravitational constant. I don't know. Sorry, can you elaborate on that? I have no idea how to do that.
No, I do not know how to do that, but I just speculate after you get some 6-point function, and you can, and sometimes we can know how to define some physical parameters. So I guess that you can see some renormalization effect in the common constant.
You mean from 6-point function?
Yeah. I guess. Sorry, I do not make sure. It's just my naive question.
Okay, I also don't know. I mean, maybe I should ask other people or my collaborator. I mean, he knows more about 6-point function. So far, what we had is a 6-point function in the spherical symmetric case. We did a calculation in Schwarzschild, but I don't know how to see the renormalized gravitational coupling. In that case, the gravitational coupling is basically a constant given by the coupling of Schwarzschild.
Okay, thank you.
Thank you.
Okay, is there any other question? If not, let's thank speaker again.